It does work, and perhaps you can hear me. I retired from this business some years ago, and there was one thing that I would have done if I'd kept on, and you've already seen it illustrated twice this morning, actually, but it's to say that a big planet, a big Earth, a super-Earth, 5-10 times the Earth's mass, would have very high pressures compared to the Earth's mantle, and a more viscous rheology, and that would make it run hot by the principle that they were just debating there, that Tozer pointed out. So I'm going to suggest that a big planet may actually not be very friendly to life, but it's complicated and you can't. Anyway, this, I looked around and there were some nice models by Tackley and others recently, which actually illustrate the point, although most modelers have focused on the question of whether there would be plate tectonics. I want to point out another thing that's happening here. As it turns out, the fourth or so author on this is Diana here. We didn't plan to quote each other's papers, but anyway, so what you're seeing is temperature on the right, viscosity on the left, and in this is a 3 Earth mass planet. The deep mantle is quite hot. The shallower mantle is cooler. The reason is, well, this is in terms of activation enthalpy versus pressure, but if you think of this as a proxy for viscosity, then this is for a model in which at pressures that the Earth's mantle barely reaches, but which bigger planets would get into, the viscosity may jump very high. It may also jump very low. So, of course, life is, as Craig said, geologists love to complicate our lives. But I want to illustrate the principle here. So just look at some of their models from the case where the viscosity is high because of the very high pressure. So they did a suite of models from 1, 3, 5, 7, 10 Earth masses. And well, this is just to give you some notion of what they look like. The viscosity plot, where it's red means high viscosity. You can see the very high viscosity zone expands as the planet gets bigger because of the much higher pressures. And the temperature scale, the temperature does rise, the scales change with these things. We'll just look at this 3 Earth mass case to see what's happening. Now, so there are those pictures again, and I've blown up this region here. What you see is this deep, very hot region, and this is a slow upwelling. It's relatively stiff. It's had to get very hot to get mobile. It's coming up, and then it goes through the transition into the much lower viscosity material, and the upwelling necks down into a quite narrow upwelling. It actually shows better in the viscosity plot, but I'm confused by that color scale. And you can see 2 or 3 other of these upwellings around if you scan this picture. Now, this mantle is heated internally, so by radioactivity. This model does not include heat coming from the core, so these are not the same as plumes in the Earth's mantle, which are generated by heat from the Earth's core, bottom heating. This is internal, but they look like plumes. There are narrow upwellings. They might be columns or they might be sheets. Now, the coloured curves here are the horizontally averaged temperature profiles through in these mantles of these various massive planets. The 3 Earth mass one gets 1,000 degrees hotter than a relevant adiabat here. This upwelling material will follow close to an adiabat, and it will tend to follow a path like this. It'll be a bit cooler, but not a lot. And it will come out 1,000 degrees hotter or more than the typical upper mantle of this planet. In the Earth, a plume comes out at maybe 250 or 300 degrees hotter than average mantle. It reaches the top, it melts, it generates volcanism. These things will be 1,000 degrees or more above average mantle. So this will be nasty volcanism, be extremely hot, extremely mobile mantle, lots of liquid generated magma. And I haven't done the fluxes. I just want to make the point. The bigger planets will be somewhat similar. Now, what are the chances? We're both quoting this old paper too, but what some people have since called a heat pipe mode of heat removal, which Tom O'Reilly and I proposed back then, is like an extreme version of what I'm talking about. This is a case where there is no horizontal tectonics, it's all vertical. Stuff rushes up, erupts, spreads out, and slowly sinks. The planets I've been showing you have horizontal tectonics probably, whether they're rigid plates or a stretchy surface, I don't know. This is tending towards the case we did there. So just to give you a rough idea. And of course on Io, you do have volcanism and quite rapid resurfacing. And that depends on the amount of heat that's being tidally generated and has to be removed. So this is not the greatest cartoon, it's from a reporter. Just a suggestion that maybe the Earth is rather unusual. Somebody talked about, what was it, marauding Jupiters that come drifting in because of gas drag or whatever, and they may scatter and clean out a lot of the inner solar system. In the case of the Earth, a suggestion by these authors recently is that because Saturn also formed and formed a resonance, Jupiter came in so far, but then the resonance caused them to crank themselves back out to a greater distance, leaving a rather depleted inner solar system, which could only make little Earths, not super-Earths. So is this true that this is another way our solar system is unique? Well, that's hard to say, but it's an interesting suggestion. And, well, the biologists have been over this, don't pay attention to any of the detail. The point is simple. From complex chemistry to the first living things is a huge jump in an emergence of new phenomena. And then from the first living possibly to the prokaryotes is another big emergence. The point is, each of these steps is a major new level of organisation and emergence in living systems, and we are, the ladder's going down, so because that's the direction you read, but we are a long way from the simple organic first living systems. It means, I think, life of some form, maybe not that uncommon, but getting to us involves a great deal and an amazingly stable planet. Where am I? So I actually went and watched Mark Hamill yesterday. In a galaxy far, far away, you might find another Mark Hamill, but it's not very likely. So The super-Earths may have persistent and quite violent volcanism. Normal Earths may not be so common. Life may be not uncommon, but multicellular life may be quite rare. Thank you.